I lost the first part of this lecture, so I'm redoing it in my office, so the two parts are going to look a little bit pasted together. But I wanted to talk about partitioning variability. So let's go through basically what is going on in the introductory lectures, but let's go through it in a much more deep way using the linear algebra. So the total variability is this quantity right here, nothing other than the just variance, the empirical variance in the y's, right? So that works out to be that right there if you work through the linear algebra. If we forget about this n minus 1, it's just a multiplicative factor. So throughout, let's not talk about the sort of mean squared error. Let's talk about sums of squares, right? In this case, the sums of squares, disregarding the n minus 1. We might call the sums of squares total, representing the total variability, just throwing out the n minus 1 part, which is just that right there. And I'm going to let H1 denote this hat matrix where the vector that creates it is just a vector of 1s. If I have a general vector, a general design matrix, let me write Hx to represent the hat matrix created by the matrix X, X transpose X inverse X transpose.
Let's make some other definitions. So the sums of the squares of error is just the residual sums of squares. So the yi's minus the fitted values, where here I'm fitting them with X. So that's that guy. And I can, because I can write that as y transpose I minus hx transpose I minus hx y, and this matrix is both symmetric and idempotent. I'll write it like that right there. Then let me define the sums of the squares for the regression model as, let me get rid of that I there, y bar minus yi hat summation squared. This is in essence the variability of the fitted values around the mean. Sort of that component of the variability that's not error, that component of the variability that's systematic variability. So that can be written, right, yi hat is equal to hx times y, and y bar, or y bar times jn, the vector of y bars, is h1 times y. So I can write this as that right there. Technically I would need a transpose there, but both of those matrices are symmetric, and so I want to write it like that. Let me work with the sums of squares regression for a minute. So note, since x contains an intercept, and we've done this before, if I take I minus the hat matrix with the x variable, the intercept is a linear combination of the columns of x. In other words, just a linear combination where I grab the relevant intercept column. So then h1 is itself a linear combination of the columns of x. So we found that this is equal to 0 whenever this matrix on the right is a linear combination of the columns of x. So, because this holds, we can write that h1 is equal to hx times h1. And we can very easily reverse that equation as well, so that h1 is equal to h1 times x. So consider our sums of squares regression again. It's equal to this formula right here. If I were to multiply out the inner terms, I get h, and I'm ignoring transpose because everything in these inner terms is symmetric. I get h1 squared, but remember h1 is idempotent, so that will just be h1. I get hx times h1, but using the identity up above this, that's just h1. I get h1 times x, which again, using the identity above it, that's just h1, and hx squared, which again, because hx is symmetric and idempotent, symmetric in the sense that I'm forgetting about the transposes, and idempotent in that the squares itself, I get that. Putting that all together, I get that y transpose equals h1 minus hx times y. Or, again, I could write it out like this as well. Remember, this is a sum of a squared things. It has to be positive. It doesn't matter if I change the sign on the interior. So let me go back to my sums of squares total. It's y transpose I minus h1y. If I add and subtract hx, I've done nothing. I've just added 0, and that's this line right here. And then I can distribute my quadratic form and get y transpose I minus hxy plus y transpose hx minus h1y. In other words, my total, my sums of squares for the total, is equal to the sums of squares for error plus the sums of squares for the regression. In other words, total variability can be decomposed into error variability and model variability. And this is the result we see in our more introductory lectures on regression, but here's how it plays out in the linear algebra. But we can take this further. First of all, in our introductory lecture, we define R squared. That's just the percentage of total variability explained by the model, SSR divided by SS total. It has to be between 0 and 1 because of how we've defined everything. But here's where I think it gets more interesting. Note there was nothing specific about H1 or Hx. These were just generic hat matrices. All that was necessary was that 1 lied in the column space of X. Suppose W is any other matrix that lies in the column space of X, and let me define HW as the hat matrix associated with W. W times W transpose W inverse times W transpose. Then just using the same logic above, that if I were to start out with Y transpose I minus HWY, that would factor into Y transpose I minus HXY plus Y transpose times HW minus HX times Y. Again, just the same logic as above. This is not SS total anymore. It's the sums of squares around the sums of squares error for that specific model. The specific model with just W. And it's saying the sums of squares for that model, sums of squares error for that model with just W decomposes into the sums of squares error if I were to add the terms to bring it up to the model, the richness of the model given by X, plus this extra term right here, this sort of regression variability on the difference between the two models, the X and the H model. We can go even further with this. Imagine if we had now an x1, an x2, an x3, and up to an xk, where let's say that Jn was x1, but then we each had a bunch of nested design matrices, nested in the sense of their column spaces. The column space of x1 was contained in the column space of x2, and so on. Okay? Then let's just take this first step, SS total, which would be y minus hx1, y transpose times I minus hx1 times y. If using the same logic as above, I can decompose that into the y transpose I minus hx2 times y plus this guy, y transpose hx1 minus hx2 times y. But now this is just the same problem again, now starting at x2. So I can go to x3 and decompose it again into these two terms. So what this boils down to is I can get that my SS total is explained by, or my SS total can be decomposed into the sums of squares, the residual sums of squares for x3 plus the variation explained by x3 over x2 plus the variation explained by x2 over x1. And we could just keep doing that. Or I could write this notation as this is SS residual plus SS x3 given x2 plus SS x2 given x1. let's suppose we kept doing that until the largest design matrix had n elements. It was a basis for Rn. Then the SS residual would eventually vanish to nothing, as we've already talked about. So what it would say is that SS total can be decomposed if our final X is a basis for Rn, can be decomposed into these serial components of variation, starting with whatever variation is explained by the lowest level model, say x1 is just an intercept, and then what if I give x2, and going all the way up to, well, I've included all n minus 1 terms in my model, how much extra do I now get when I include the nth term?